Okay, we're going to go on with chapter 6, circular motion and other applications of Newton's laws. In this chapter, we're going to combine our knowledge of circular motion with that, with what we already know about forces. We're going to discuss reference frames further, and we're going to talk about resistive forces that are speed dependent. The resistive forces we've talked about are friction. We're going to expand that to resistive forces that are speed dependent. So let's go on. Let's see. This figure is a figure of a particle in uniform circular motion. The particle moves with constant speed v in a circular path of radius r. The acceleration is, the centripetal acceleration is v squared over r. Centripetal acceleration is directed towards the center of the circle. And note that the centripetal acceleration is always perpendicular to the velocity. If there were a component of acceleration parallel to the velocity, then this particle speed would be changing. We'll get to that later. We extend the particle in uniform circular motion to incorporate the concept of force. Consider a puck of mass m tied to the string of length r moving at a constant speed in the horizontal path, the circular path shown in the figure. The weight is supported by the normal force from the frictionless table. The string anchored to the peg at the center of the circular path causes the puck to go in a circle. Why does the puck move in a circle? Newton's first law says the puck would move in a straight line if no force were acting on it. The string prevents the motion along a straight line by exerting a radial force, F sub r, towards the center and causes it to go in a circular path. The force is directed along the string toward the center of the circle. We apply Newton's second law along the radial direction. The sum of the forces equals mass times centripetal acceleration equals m times v squared r. We're going to see that quite often. A force causing centripetal acceleration acts toward the center of the circular path and causes the change in the direction of the velocity vector. Okay. Let's see, when the string breaks, the puck moves in the direction tangent to the circle. It doesn't keep going in a spiral or anything like that. It just goes in a tangent to the circle. If the force vanishes, if the string breaks, the puck moves along a straight line tangent to the circle. So let's take a little quick quiz. You are riding on a Ferris wheel that is rotating with constant speed. The car in which you are riding always maintains its correct upward orientation. It does not invert. What is the direction of the normal force on you from the seat when you are at the top of the wheel? Is it upward, downward, or impossible to determine? Well, it's upward. If you're not flying off the seat, if you're on the seat, then the normal force is supporting you. It's upward. Now, same problem. You're riding on a Ferris wheel that is rotating with constant speed. The car in which you are riding always maintains its correct upward orientation. It does not invert. What is the direction of the net force on you when you are at the top of the wheel? The net force, not the normal force, the net force. What is the net force when you are at the top of the wheel? Well, it's downward. Again, unless you're flying off the seat, it's downward. Okay. Yes. All right. Okay, we'll stop here and continue with an analysis model and some examples.